Okay, so yeah, it's a pleasure to be here at the Simons Foundation. Thank you all for braving the tremendously awesome weather. For a San Diegan to see actual raindrops falling is quite impressive. It's worth the trip just to see that and to feel that. Normally what we see when we're in San Diego looks like this. Blue skies, smiling faces. I always encourage people when I give colloquia or seminars, this is what you want to think of when you apply for graduate school, okay? Come to a place like this or postdoc. Come postdoc and spend time and study San Diego. So today I'm going to talk about something that you might have heard about, you might have thought might be solved, or perhaps people are really making great progress in this field. But I was thinking it's actually a very exciting time to be a cosmologist. We don't get that much money, especially those of us at state universities and states like California, but we get to work with the coolest, smartest, most energetic young people in the world. These people here are the people that really make my job worth doing. So it's a great treat to be able to do that. And we've come up with some really cool ideas and fun things to test. And a lot of that is now currently being sponsored here by the Simons Foundation. I'm going to talk to you about that research. And it's really a unique treat because some of the research that we're investigating, just serendipitously, happened to have been created unintentionally by Jim Simons. And I'll talk about those connections and show some embarrassing old pictures of Jim. No, they're not that old, but really it's quite exciting to be able to do that. And as I said, it's quite serendipitous as well. So the talk is called The Twisted Universe, and that's really not an accident. We're looking for a special type of behavior of the light, of the radiation, the oldest light in the universe, called the cosmic microwave background radiation. And it's an invisible glow that bathes us like we're at the center of this very benign oven that's only 3 degrees above absolute zero, thankfully, so significantly colder than here in New York today. But what we're able to do with this is actually investigate properties of the universe that we're otherwise blind to. And so what do I mean by that? Well, the properties of photons. Photons endure. We believe they have infinite lifetimes. At least we have no credible reason to think that they don't exist forever. So the question is, what happens to photons since their birth as they're traveling throughout the universe to reach our detectors in the Atacama Desert, the South Pole, etc.? What happens to them? Well, a lot of things happen to them, thankfully, because the fact that they're the oldest photons in the universe allows us to learn about what the universe was like since their birth to their detection, from 13.8 billion years ago to today. And perhaps even beyond, even to a trillionth of a second after the Big Bang. So they get scattered, they get manipulated, they get deflected, but one property of photons endures, and that's called their polarization. So the polarization properties of photons are perhaps their most enduring property. And to illustrate this, I like to talk about the fact that everybody here has a sixth sense. Okay, not like this guy in this movie, but actually we have the ability to detect polarization. We detect color, which is frequency. We detect intensity via the isotropy or lack thereof. But we also have the ability to see polarization of light. And most people don't recognize this, but we do have a sixth sense. And that's shown here on Bruce Willis's head. And this is called a phenomena. It's related to the properties of our eyes and the retina itself. And I'm going to demonstrate for you this phenomena. And it's actually one that I didn't realize I had, and so most people don't realize that they have, but it's actually the ability to sense the orientation of polarized vectors from light scattering in the atmosphere. So here's how you do it. I'm going to show this pattern. This is called Haydinger's brush, named after this I think it was an optician in the 1800s in the UK. And it's a responsibility of, or it's the result of the dichroism, the birefringent quality of the macular in your eye, and this pigment called xanthophyll. I'm sure some people here at the foundation study such things. And it's the fact that this is polarization sensitive. So if you look at this image here, this brush, I'm going to take away the text. Now look at this picture for a little bit. I'm going to take it away, but it's going to appear that it remains for a little bit. And that's this phenomena of this persistence of the polarization sensitivity of the macula. So I'm going to take it away. Do you still see it? So it might take a little while. So I'll take it away, and I promise it goes away instantly, as fast as PowerPoint will allow me to remove it. Here we go. And you might see the inverse of it. You might see where it was yellow, it's blue, and where it's blue, it's yellow. That's the fact that your eyes and the screen are actually polarized, hopefully. So if I rotate this thing, it gets slightly dimmer, slightly brighter at 90-degree differential orientation. And that's because the screen is polarized too. So your eyes are polarized very weakly. Okay, you're not going to, defeat Google Maps with your ability to sense polarization like some birds do. But yet, we have the sixth sense. And what if we can apply this other sixth sense, which is really using our brains, to think about the very, very early universe and study it using the most enduring property of the photon, its polarization? It behooves us to try that and ask, does that polarization pattern stay fixed as photons fly for billions of light years, tens of billions of light years, or does it somehow get modified? And does that modification of the plane of polarization teach us something about the universe, or, more excitingly to me, general relativity, special relativity, and the properties of light? So this is a cartoon that we made for the BICEP announcement a couple of years ago. Caused a lot of fanfare, and I'll talk about that. This was the detection that our team believed we had made when we imaged this swirling, twisting type of polarization in the cosmic microwave background's polarization. So this caused a lot of fanfare. I'll talk a little bit about that. But really the reason why it's so interesting is that we believe that there's an imprint of the first trillionth of a billionth of a second after the Big Bang in its polarization. So things called gravitational radiation, which we know exists, we've detected waves of gravity via, not directly yet, although LIGO seems to be rumored to have a detection in the wings, waiting in the wings. Nevertheless, we've seen the evidence that gravitational waves exist. And so if gravitational waves are like photons, they have infinite lifetimes too. Therefore, we can use the universe as the ultimate gravitational wave detector. This is the idea that some of us had back in 2001 when we proposed to build the BICEP 1 experiment. We didn't call it BICEP 1. We didn't know there'd be a BICEP 2. We just called it BICEP. And it really relates to the properties of this cosmic background of photons to act as a giant detector of waves of gravity. And that's what we believed that we had done. I'll come back to that story in a little bit. Basically what we do is we image the cosmic microwave background. This is a map of the full sky, if you could see microwaves, by the Planck satellite, this billion-euro experiment that just really finished up and is wrapping up results now. And it shows that when you have a pattern of photons, which is not isotropically distributed, they'll scatter off of the electrons in the primordial soup. And that will create polarization. Just like the scattering of light in this projector or on a projection screen causes polarization weakly too, as I demonstrated earlier. You can take this polarization pattern and decompose it into two different patterns. So you mathematicians here will recognize this basically as a version of Helmholtz's theorem, where you can decompose a field of vectors into a part that looks like the divergence or gradient of a scalar field, called that E-mode polarization. Or you can decompose it into something that looks like the curl of a vector field. We call that, not surprisingly, curl mode or B-mode polarization, and that's the origin of the word BICEP, which I cornily coined back in 2001, which stands for Background Imaging of Cosmic Extragalactic Polarization, because it's the muscle that you use to do curls. Okay, it's very corny, and I haven't been allowed to create an acronym since. The Simon's array is as close as I get. We take this pattern on the sky and do Helmholtz's theorem. We decompose it into these two different scalar potentials, and then we map out that scalar potential on the sky. These are maps made by my postdoc, Grant Tepley, who's now at San Diego. And we imaged a very small region of the south polar hemisphere, the hemisphere that you can see from the South Pole, that we thought was far enough away from the galactic plane to be immune from the contaminating effects of galactic dust. Turns out we were wrong. But based on the information that we had when we selected this patch back in 2004, this was the best region to look for. This was all the information we had. The whole sky is not visible from the South Pole. Only about 1 or 2% is as clean as the patch that we measured. And it just so happens that it wasn't the cleanest possible region that exists. Nevertheless, it was very good, and we have detected these patterns with BICEP 2, and in fact, we have more confidence in these results than ever. Unfortunately, we're getting more and more confident that the signal is really a contamination signal due to foreground contamination from these molecules of dust that I'll talk a little bit about later. So getting around that contaminating signal is the goal of the future experiments like Polar Bear and the Simon's array. For the cognoscenti in the audience, I'll just say that we take these images, these colorful patterns, we decompose them, we make a power spectrum of them, the Fourier transform or the autocorrelation function, and we plot these things in terms of these multipole moments, the coefficient of the spherical harmonic corresponding to a given scale of angle on the sky. I'm not going to talk too much about this. Suffice it to say this type of work has been really perfected by many of our collaborators in the field, And the formalism is very well developed, and we can extract from it a great deal of information. Before showing you what we know about the universe today, I want to just harken back to 23 months ago in March of 2014. So we claimed detection of this swirling, twisting pattern that's fancifully rendered on this image up here. So you can see this twisting pattern, and it was indicative of B-mode polarization, and it still is, because we have more confidence than ever that the signal is real. The interpretation has radically changed, though. It has gone from being a harbinger of gravitational radiation to being literally dust on the lens cap, almost, of our experiment. Not on the lens cap, but in the sky. So we create a lot of headlines here in New York. The greatest scientific newspaper in all of science is, of course, the San Diego Union Tribune. Okay, and that had a lot of zeros here because we thought that this was indicative of a measurement, a trillionth of a billionth or so after the second after the Big Bang. I like this headline down here. Just kind of harkens that, some guy sees the beginning of the universe. Some guys just, well, oh my God, there's the beginning of the universe. We published this paper. It was a 23-page letter in Physical Review Letters, which is known to only publish letters that are 4 pages long. But it was published last June, or 2 years ago in June. And it created a lot of fanfare. And so now I want to talk about some of the fanfare that you may have heard about, the so-called Nobel Prize. So it's little known that we are attempting to measure inflation, but people don't realize that the Nobel Prize has already been awarded for inflation. Not to Alan Guth, the forecaster of inflation, but rather to a more familiar, perhaps to Jim and others here, a more familiar type of inflation, namely economic inflation. So Milton Friedman won the Nobel Prize for discovering the connection between inflation and unemployment. So if you read through here, it's really great, and he has this great discussion. But I realized after our BICEP 2 paper came out, we actually were curing unemployment, maybe for several of you here, because we had 1,200 citations as of last night to that paper. So we now have ensured full employment for theorists. So you're welcome. Okay, so getting back to these citation counts, I always like to point out my favorite citation of all is in The Onion, the scientific paper of record. Correct me if I'm wrong. So this says down here, we can observe long-term phenomena like the CMB's B-mode polarization and the connection between India Arie and her man, all of which seem to have existed since the universe's infancy. And up here they have real, your neighbor around the corner, Michio Kaku, is up there, as is Aretha Franklin. So it's bringing together these multiple cultures, these distinct cultures. Now, where are we with the universe? So we actually know things about the universe far more precisely than ever before. When I started grad school in 1993, we didn't know if the universe was 10 billion years old or 20 billion years old. We didn't know what the universe was made of. We didn't know about dark energy at that time, 1993. Now we know that the universe is flat. It has flat spatial geometry to within 0.5%. That precision is astounding. There's a famous quote, I think it was Landau, who said, cosmologists are often in error, but never in doubt. But now we're actually doing high precision science. Some of these things we now have a 10 sigma detection that the matter in the universe is non-baryonic. The preponderance of matter in the universe is non-baryonic at 10 sigma significance. It's just incredible to see this change in 23 years. Is phenomenal. So we now understand the model of the universe is described by just 6 parameters. And that's quite astounding. Here are some other things that we're doing with the microwave background. Out in the hallway, you have a picture of the standard model of physics. There's 17 different particles on that list. There's leptons, there's a Higgs boson, etc. But there's 3 particles on there, only 3 out of 17, whose masses we don't know anything about. Well, I shouldn't say we don't know anything. We don't know what the masses of the 3 neutrinos and their antiparticles are. So really, 3 different particles' masses are unknown. Elementary particles. This is stuff that's been known for other particles for dozens of years now. So we're closing in on the mass of the neutrino, and that's one of the prime targets for the Simons Array telescope. And the next generation, which we call CMB stage 4. I'll talk about that at the very end. And the last thing is, how are we doing on inflation? How well do we understand how well motivated is inflation? So here's a scorecard. Here's like a report card for inflation. And I always say, if I brought home a report card like this as a kid, I wouldn't have been grounded so much. I mean, you know how often I was grounded. But this is actually passing so many different tests. It's incredible. We have so much circumstantial evidence for inflation. But as you know, you lawyers in the audience know, circumstantial evidence is not sufficient for conviction. We want to prove that the Big Bang originated in this inflationary explosion. Well, really the only way to do that is, we think, to detect these gravitational waves. So that's really the prime focus of this hunt that we're going on at this moment. The last thing I want to talk about are foregrounds. Foregrounds are the contamination, the dust that's in our galaxy between us and the Big Bang itself. And this can mimic the pattern of polarization that would be produced from gravitational waves emanating from the Big Bang. So we're attempting to measure this foreground more accurately than ever. So this just shows, this is a slide made by our colleague Lyman Page. It just shows the difference between the BICEP detection after removing dust and before removing dust. And this is, like I said, Nobel-worthy science. So we're really attempting to measure this incredibly small signal. If you look on this scale here, you may not appreciate, all the features of this plot. But note the scale on the left-hand side is in microkelvin, fractions of a microkelvin. That means we're looking at signals that are only a few dozen nanokelvin, a few dozen parts per billion of the background. It's just phenomenal. And this technology has really improved, and I'll be passing around, as risky as it is to pass around hardware in a room full of theorists and mathematicians, I will do it. I'll pass around some hardware later on. So what I want to talk about today is not inflation and not neutrino masses. So if you're interested in inflation and neutrino masses, I'll give you a second to leave. But really, what I want to talk about is physics beyond this astounding physics that I just described. But nevertheless, this to me is a new pathway, a new direction in physics that will allow us to test and really poke at the physics that we claim we understand so well. So this is the Polar Bear Telescope, a documentary on BBC that's showing us scanning away like a sentinel in the dark Atacama Desert night. What I'm going to talk about are a few different phenomena that are really intriguing to me. And really they center around the extensions to the so-called standard model, the 6-parameter model that seems to fit the universe so beautifully. How can we extend that and go beyond that model and look for cracks and flaws in our understanding of nature? That's what's so exciting to me today. So I thought about doing this when I was coming in today, because what I'm going to be talking about is how this plane of polarization of photons rotates as it travels from the Big Bang last scattering surface to us today. It's called cosmic polarization rotation. I got the nickname from this police car. I saw CPR. I thought that was kind of cool, cosmic polarization rotation. So we started to think about how to test the underpinnings of physics. The most basic underpinning law of physics is Lorentz invariance. It's the foundation of special relativity, which is the foundation of general relativity. The way to look for perhaps new signals, new physics, is to look for ways that you could perhaps reveal cracks in the standard model. So the way that we're attempting to do that is signified here. So this is a slide from my friend Matt Muse at Cal Poly, and it really shows the building blocks, like my kids like to build these wooden blocks. But if you just move one of these little blocks, you break, say, Lorentz symmetry, you actually have a rippling effect. Not from gravitational waves, you have a rippling effect throughout all of physics that might suggest that perhaps Lorentz invariance is not respected, which would mean that we don't understand special relativity even. And this is high risk, maybe high reward physics. It's extremely interesting. And the ramifications have never been tested before because we haven't had the technology to do that. And there's my colleagues and I, some of whom are in this room, are looking at ways that we can precisely test the underpinning Lorentz invariance or lack thereof in the universe. So I'm throwing some red meat to the theorists and mathematicians. This is the standard model of physics, along with a couple of different types of so-called extensions to the standard model that you could do. You could violate the standard model, and the number of ways to violate the standard model are infinite in number. However, you can classify the ways that you could break them into different types of parity violating signatures. So I'll leave you a couple minutes to write these down. No, I'm not going to even investigate this. It's just some red meat, as I said. But here's where Jim comes in. Because if you take the standard model of physics, which is undergirded via this so-called Lagrangian, which demonstrates, say, the underlying physical laws of electromagnetism, and you were to say that electromagnetism in vacuum, in the interstellar intergalactic medium, has some way of distinguishing between the polarization of light, of one polarization versus another, then you could look for Lorentz invariance. You could look for violation of this Lorentz invariance that we hold so dear as physicists. And the way to do it was really suggested by Jim. Again, it wasn't really what he was planning to do. It was a serendipitous discovery that really is related to these Chern-Simons forms, these topological sort of characteristic forms, that when you add them to their analog in the special relativistic description of space-time, can cause a different propagation constant for left-handed polarization versus the right-handed polarization. And that gives us a chance to test extremely accurately how well does the universe respect the laws of parity conservation. The physics behind this was first developed by Sean Carroll and Field and Jakiv in the early 90s. And really it lay in waiting for a very long time because we weren't able to test with any degree of precision whether or not this Chern-Simons-like addition could produce an observable signature. Now we're at the level where we can test this tiny variation. It's kind of like giving the mass to the photon in the right circular state, but not the left circular polarized state. And that's really exciting, and that has implications for axion searches as well. Here's a cartoon of what would happen if you had such a phenomena. So you'd start off with vertical polarization. This teal-colored line is oscillating vertically. And by the end of propagation through a medium that's birefringent, you get this twist, this rotation, the twist in the universe itself. And we don't have very good constraints on that. I'm going to pass around a piece of this crystal. This is calcite. This is Iceland spar. And if you put it over this box and then you put a Polaroid in front of it, you'll see that it's birefringent. It has two different indices of refraction. So one type of polarization will go in one direction, one will go in the other, and you'll see it as if it's split into two blurry vision images, but then you can suppress one of them with this Polaroid. So I'll pass this around, start with Jim. Yeah. Now, what might predict such type of phenomena to occur? It's one thing to describe it if it occurs, but why would we expect that to happen? Well, there's a lot of models that have some similarity, I believe, and the theorists in the audience can correct me if I'm wrong later, but there are similarities between, say, the Higgs mechanism and mechanisms to generate this fundamental asymmetry between helicity states of the CMB's polarization. So there's models, there's a 35-page paper with like 800 equations that classify all the different ways that you can violate parity using electromagnetism, photons. And that's what we're searching for. Now, what would that look like if you had such an effect? Turns out such an effect has already been reported, also in the New York Times, also on the front page of the New York Times. So it said back in 1997, it said, this side up may apply to the universe after all. That's kind of cool. I like to look at old headlines in the New York Times and see who is still in the news. Okay, so you still have Netanyahu. He's still in the news. This is almost 20 years ago. There's Newt Gingrich. You find him in the news. Some things are invariant, right? They're, the Middle East conflict. That's just, you could have 200 years from now, you'll probably have the same headlines. So that's kind of cute. And let's zoom in on this headline. So they claim by looking at distant galaxies that they could see the twist in galaxy polarization from radio galaxies. And they claim this is a very significant detection that validated this discovery, this claimed discovery of Chern-Simons-like electromagnetism. And it lasted for a while. And I like these quotes here. Here's Jim Peebles, who's just down the road in Princeton. And he's still around. He still says stuff like this. His favorite, his go-to line when somebody has a front page in the New York Times, he'll say the same statement. It would be really a profound change in physics if it's true. Of course, it didn't turn out to be true. It was a statistical fluke, a poor analysis. It was corrected by Sean Carroll and others and found to show no evidence for the effect. But I just want to point out how hard this measurement is to do using radio galaxies. They were claiming to look for an alignment of polarization at right angles to one another. So you'd expect to see two peaks, one at 0 and one at 90 degrees. And the only thing I want you to take away is how coarsely grained this histogram is. It's in tens of degrees. That was the precision that they could get to. With the CMB, for the first time, we're able to get down to tenths of degrees to really probe if this is true or not. And I'll explain that towards the end. I said I like to do high-risk physics. I also like to do low-risk physics, right? It's one thing to be risky and take a lot of chances. But it's good to do something, to make sure that you can pay the bills. And the way that we're attempting to pay the bills with this type of measurement is to constrain primordial magnetic fields. Magnetic fields are ubiquitous in nature. From people, we actually have small magnetic fields in our bodies. all the way up to planets, solar systems, galaxies, stars, planets, everything in between, and clusters of galaxies. And in fact, the clusters of galaxies have magnetic fields that are tremendous by cosmological standards. They're much, much smaller than our body fields or the Earth's field. They're micro-Gauss level fields, fractions of a millionth of the Earth's field. So these are tiny fields, but by cosmological standards, if you think of how many galaxies there are in the universe, hundreds of billions of galaxies, and you add up how much space, how much volume there is in each galaxy, it's a tremendous amount of energy stored in magnetic fields. Where did those magnetic fields come from? So my plasma physicist friends will say, oh, you fool, it just comes from dynamo activity. You get some charges swirling around and you generate a magnetic field. It turns out any model that tries to predict how big or small the seed field is cannot produce a field by, say, the redshift where we observe these galaxies. There's not enough time in the universe to spin up a cluster of galaxies to have the fields they observe via dynamo action. So we suggest that there must be some primordial seeding field, and there are many models that suggest this would be so. And there's some people that I put up some limiting, some upper limits on this field. With polar bear, we've set the most stringent limits on how big an early cosmological primordial field could be. So these are ubiquitous throughout nature, and yet we don't know how they get started. Another embarrassment, if you will, for physics, but it gives us, experimentalists, it gives us a chance to actually go after something that should be there by all rights. And if it's not there, that's even more exciting in some sense. It's really a deep mystery. I just want to show you what these fields look like. This is M51, the Whirlpool galaxy. The question is not if these galactic fields exist, but how many are there, how many fields there are, and how strong these magnetic fields are. So the first step is to go out and look for it. And it turns out that the CMB provides us a prediction of what you'd see and how a mechanism to unravel what the signature would look like. It turns out there's a lower limit. So we have upper limits on a lot of things in physics, like the amount of gravitational radiation in the universe. We also have a lower limit on how big the fields could be. People believe that there's a mechanism that's preventing fields from being smaller than this admittedly fantastically small number of 10 to the minus 16th Gauss. So that's a billionth, almost a billionth of the signal that we're able to constrain currently in the microwave background. Nevertheless, when you have a lower limit, it gives you some hope. You have an upper limit and a lower limit. You just have to tighten those up until you get a detection. So this lower limit, I won't go through it. It's actually a fascinating limit. It's a result of sort of a no-go theorem that if you had a universe in which there were no primordial magnetic fields, then you would expect around these objects called blazars, which some of us here in the audience study or know about, these very bright quasar-like objects, you expect to see a halo surrounding them from the interaction of these positrons produced by this upscattering when they interact with the CMB photons, which we know how many there are in the universe. There's 419 per cubic centimeter. So around each one of these blazars over here, you should see a glowing halo of gamma rays. We don't see that. Therefore, we infer that a magnetic field is causing these electron-positron pairs to divert from one another. This is the way that we get that fantastically small, but nevertheless existing lower limit. So we have an upper limit and a lower limit, and that gives us, experimentalists, an important threshold to target. Now, are these crazy things? There are people in the audience here that study these in depth, very respectable people. and in fact, we're trying to go after these things, predictions by people like Ed Witten and David Spergel and Stefan Alexander, et cetera, to go after this incredibly small magnetic field that we think can only reveal itself by the presence of this rotation of the CMB's polarization. So I'll just summarize with where we are with this polarization rotation, this Chern-Simons-like rotation of polarization. This is undergrad Kelsey Lund at UCSD just made this compilation. This first paper was in 1990. It lay dormant for many years. Then the New York Times article hit in 97. Then nothing happened. And then we started to get interested in it in San Diego and elsewhere. And now it's really ramping up and taking off. You know, as much as you can consider something in physics taking off. You know, this is not viral by internet standards, right? But now we're at the level of sort of the degree level. So the radio galaxy that led to this claim in the New York Times was at tens of degrees. We're now 10 times more precise, and we believe, with our colleagues at Columbia, Brad Johnson et al., and we'll talk about that proposal in just a minute, that we can get to 10 times smaller than these limits, which would really put pressure on models of early magnetism and Chern-Simons effects. This is a claim that was made using early BICEP 1 data that claimed a detection at 3 sigma of a violation of CPT invariance, which is an allied thing that comes concomitantly with the polarization, rotation, and Lorentz invariance. So we refuted this in a paper we wrote in 2014, and it really put us on a path to discover what we could learn about this rotation of polarization in the cosmos. And the way to do it is to build an instrument that's incredibly sensitive, that has multiple frequencies for foreground elimination, and we also do a very, very high-level statistical analysis to preclude false detections and false positives. As Feynman said, you have to be careful not to fool yourself, and you always are the easiest person to fool. So as long as you think about Feynman, you'll be okay. You always have to assume that you're going to want to be biased to see something that you're looking for. So we avoid that using these tools called null tests that I'll talk briefly about. So this is the Polar Bear Telescope. It's a big collaboration. It's the world's highest cosmology telescope. I know there are people here from the ACT experiment, but the ACT experiment is 10 feet lower than the Polar Bear experiment. Okay? So we are technically the highest CMB experiment in the world, on Earth at least. And this telescope has been going on for 4 years exactly as of this month. And it's a relatively big collaboration by these, my thesis project was with 3 other people. Now we've got almost 100 people on this project, but it's really needed because we're building an incredible instrument that's as sensitive as possible to these systematic effects, but is also going after these signals which we know must be there. So this is our team meeting at Berkeley last summer, and we have a big team. We're located in Chile, 5,200 meters, about 17,500 feet. It's like being on another planet when you go there. The South Pole is amazing to go to and beautiful, but you see things like llamas walking around at 17,000 feet. It's pretty impressive. I get out of breath walking down a flight of stairs at 17,000 feet. So we can look and cover almost the entire sky. 85% of the sky is accessible from our site in Chile, which is important. And we can also overlap with fields that are studied by optical astronomers, ordinary astronomers looking at galaxies and galaxy clusters. And that allows us to do very, very detailed, important cross-checks on our data for the systematics that must be lurking there. So we actually are able to modulate our data. We use what I call God's modulator. You always want to do something in physics. Dickey showed you want to do something that modulates your signal that only you can pick out through a clever choice of hardware or software or both. And we use the Earth's rotation, which if you think about as an object that's polarized rotates, its polarization vector as it rises and sets also rotates. And you can use that phenomena to distinguish between a real polarized signal and a systematic effect. So we observe for thousands of hours. We observe, you can see how dark the sky is there. We're above half the atmosphere. So you need to wear oxygen in your nostril, these cannulas in your nose, walking around with scuba tanks full of oxygen on your back. And you do that for weeks and weeks at a time. And we made several different important discoveries with this telescope that I'll talk about. I also brought some of the pieces of the telescope that we are no longer using. It's a giant telescope. It's 11 feet across. It weighs about 80,000 pounds. And we're actually building 2 more copies of this telescope in the next few weeks, and I'll talk briefly about that later. So light comes in from the universe, bounces around, and gets detected on these arrays of detectors that I'll pass around as well. These detectors are shown here. These are made at Berkeley's clean room, and what they have are little tic-tac-toe boards. And these little tic-tac-toe boards determine and filter the polarization of the CMB very, very precisely. They're only done at 1 frequency, and that's a limitation of this project that we're now remedying with the Simons array. So we take this array. These are little contact lenses that my group makes in San Diego. We attach these to the detectors. We cool the whole thing down to 250 millikelvin, 0.25 degrees above absolute zero. I'll pass these around over here. These are our detectors. They work on a very simple principle, which is called the principle of using a bolometer, is one that simply makes use of the fact that light is heat. Heat can warm up a substance. You can measure the change in temperature of a substance via its resistance. So we measure how the resistance of an object that's called a superconductor, how it changes with response to the temperature that comes in. And because we have 1 detector for each polarization, that allows us to distinguish how polarized the sky is in a given direction. So we published several papers in 2014. We actually made the first detection of this BB polarization at small angular scales just a week before the BICEP 2 announcement came out. And we've also proven that this B-mode signal exists with very, very high level of significance. And I refer you to these papers on the web. I can talk about them in more detail. The most recent paper that we produced is this one. And this is the tightest constraints ever made on the strength of a primordial magnetic field. So we use the fact that a primordial magnetic field will rotate the polarization in a very characteristic way as it travels from the last scattering surface of the CMB to us today. And that rotation pattern, we mapped it out on these patches of the sky from Chile. And that showed us the lack of observation of this effect, showed us that the primordial magnetic field strength has to be lower than about 4 nanogauss, 4 billionths of a gauss. This is roughly a billionth times smaller than the Earth's field. So these are fantastic magnetometers, in some sense the most sensitive magnetometers ever made. What we think we can do is at least a factor of 10 and maybe 100 times better than this result with the upcoming Simons array. And I'll just show you, remind you of this slide here that I showed earlier. What we're now doing is looking at different terms. My graduate student David Leon in San Diego and I are looking at ways to extend the standard model that are still consistent with current data that can be tested very precisely with our upcoming measurements. I want to get down to the last major project, which is a space-borne proposal that Brad Johnson from Columbia and I are proposing to the NSF currently. Doing how many weeks, Brad? This is a small satellite, and it's done to create something which has never been done before. We measure the CMB's temperature. We compare the CMB constantly to the temperature of Jupiter. So we know the temperature of Jupiter. We've been to Jupiter, not me, but we've been to Jupiter. We've stuck thermometers inside of Jupiter. We know how hot it is. We know how big it is. We know how far away it is. That's very easy to calibrate your instrument. There is no equivalent thing for polarization. Most people are shocked by this. They don't realize that there's no standard candle for polarimetry. So we're endeavoring to build one. And we're really guided by the first measurements done with this object here. Very few people recognize this, but this was actually the first internet portal ever in history. So this was a balloon. It was basically coated in metal, and it was launched over the middle of the United States. It flew up to the upper stratosphere, several hundred kilometers up. And from there, you could reflect waves of light, or radio waves, from Pasadena all the way to the East Coast in Bell Labs. And those of you in the know will recognize this telescope here is the same one Penzias and Wilson used to discover the CMB itself in 1965. Or just 50 years ago, it was discovered. What they were trying to see was the internet. They were working at Bell Labs, Ma Bell, the telephone company. They were looking for this signal. They couldn't get away from the static. And even we don't recognize what static is. I talk about static to my 18-year-old freshman at UCSD. They, what is static? YouTube doesn't get much static on it, right? But it used to be that you had to tune in television stations in order to see them. They couldn't tune it in accurately because there was too much static. Well, it wasn't static, of course. It was the universe. It was the heat from the Big Bang, the fossil relic of creation, and that was radiating down on us in all directions. And they famously went in and they found pigeon droppings and they shooed away the pigeons. Then they couldn't get rid of the noise. The pigeons came back, so they shot them with a shotgun shell. And I once asked Arno Penzias himself, how did you get the money from the NSF to get that shotgun shell? But he wouldn't answer. So this was really all that there was. And the way to make the detection that Penzias and Wilson improved upon is they built a very precise calibrator. And that's what we're trying to do with the CalSat project, which is what I'll talk about next. So it turns out a guy named Ed Ohm actually measured the CMB, 3 Kelvin, and he didn't realize that what he was seeing was this echo of the Big Bang, as I said. He thought it was just extra noise. And he said, I'll just throw it away. I'll make my error bars bigger. And that's what he did. And he threw away this 3 Kelvin signal. And what I always say is that's the first case of really losing the Nobel Prize. You hear about winning the Nobel Prize a lot. That's how he lost the Nobel Prize. So here they are. They won the Nobel Prize in 1978 from controlling a systematic error. One of my mentors, David Wilkinson, who passed away, my advisor's advisor, he used to say, when you want to do an experiment, when you don't know what to do, just do a very precise experiment, and you'll be really fascinated by what turns up. So what we're trying to do is really is compress this diagram here, which shows all these detections, if you will, of a rotation of cosmic polarization. But we believe this is contaminated by systematic errors. So how do you get rid of them? These miscalibrations cause a false signal to originate. So we've come up with Brad Johnson and his group at Columbia a way to calibrate the CMB that doesn't use the CMB itself, as we proposed in San Diego several years ago now, but actually it allows us to propose, not the self-calibration, and not to use any astrophysical source that could have frequency dependence, could be itself contaminated by dust, but instead to build our own calibrator, and that calibrator will be launched on a small satellite. So here are some of the parts that we're going to use for this satellite. There's two different incarnations of it. First, we're going to make one on a balloon and fly it over the Simons Array in Chile. So here's a cartoon that we made that shows a calibration source shining down onto our telescope. And this would be a small experiment, and we could get to a factor of 10 times below the limit that's constraining us currently. So that will be an important improvement and a huge step forward. The next step, the ultimate step, is this CalSat satellite that Brad has been working so hard on for the last year or a year or two. And it's really a CubeSat, which is an inexpensive small satellite launched by either NASA or SpaceX or some other platform that would go into low Earth orbit. And as the Earth turns underneath the satellite, would illuminate every observatory that's looking at the CMB's polarization. So this tiny little satellite, a cubic foot of satellite, which would be less than $1.5 million probably to build, this satellite will cover the whole Earth, make for a perfect calibrator for this type of phenomena, and would allow us to make, if true, a 20 sigma detection of this polarization rotation effect. So if that's true and that does happen, that would be quite astounding confirmation that perhaps Lorentz invariance is not respected at the highest levels. And some people have motivated Lee Smolin and others that because we know that the weak force violates CP, that violates charge parity conjugation, and all the forces must have been unified at the Big Bang, that all the forces have a tiny bit of parity violation within them, lurking deep, and we have to tease out that signal by following David Wilkinson's advice of looking for very, very precise phenomena. So this is really the last couple of slides that I want to show. The foreground contamination is very important to resolve in the light of BICEP. So to do that, we're building 2 new telescopes and a brand new type of detector system that's never been done before, and they're really quite cool. So this is the telescope. This is Simons Array number 2, the second of 3 telescopes in Italy where it's fabricated, and it's being shipped to Chile through the Panama Canal. This is what it's going to look like when we assemble it. It's very nerve-wracking when you have this ginormous piece of metal and you're lowering it down, and there's just 2 guys with ropes, holding this thing that you've spent 10 years of your life working on. But nevertheless, it works, and we're confident that we'll be able to deploy it. Again, everything is a lot harder at 17,500 feet. We often have to call up people at home and say, can you check my arithmetic? Is 7 plus 3 10? I mean, your brain goes totally haywire at high altitude. You have problems with your vision, even with oxygen. So it's quite an alien landscape to be on, and you have to do everything by yourself. You have to bring your own concrete up there, your own plumbing. We have these flammable toilets that, don't ask me exactly what they do because it's not for a polite company. But you have to do everything and bring everything in and out by yourself. So it's quite an alien landscape to be in. The really enabling technology was invented by my partner in crime, Adrian Lee at UC Berkeley. And it's this fascinating type of detector. So these detectors, I have a prototype of them here you can see after the show. And they are lithographed on silicon wafers. And they have this beautiful spiral pattern in it. You remember the polar bear detectors? They look like little tic-tac-toe boards. Anything that's electromagnetically active that has a characteristic length will be narrow frequency. Won't be good for looking for foregrounds. But if you make a fractal antenna, this is a fractal antenna. It has scale invariance. If you cross your eyes, or if you're at 18,000 feet, and you look at this thing and you blur, you can't tell where you are. You feel like you're falling into it. That's because it's a fractal. It's extremely broad bandwidth. And what Adrian realized is that you could use these to make detectors that could tease out the dust from the CMB. And that's the name of the game right now. It's very prescient that he began to work on these detectors several years ago. So these detectors make detections of 2 different frequencies or 3 different frequencies at both polarizations. You can kind of see that one of these lines is more bulbous than the other, and that's to get the polarization, the linear polarization of the CMB. And so these are unique detectors that we're deploying not only in our experiment, but also are being used by our competitors, the South Pole Telescope. So we have the camera, looks kind of like a giant DSLR camera, right? Except it's about 1,000 times more expensive. And these detectors are cooled down to 0.25 Kelvin, and there's 8,000 of them in this little chamber over here. Not so little, maybe almost 2 meters long, as opposed to Polar Bear 1, which had only 1,000 detectors. So each one of these new telescopes will be 8 times more powerful, and we'll have 3 of them. So we'll have 22,000 plus detectors, going from 1,000 to 22,000. Here's what they look like. Here's our friendly competitors at Chicago. They are also building detectors based on our design, this fractal pattern. They can see as well as we can. They're looking at 3 channels. We're going to look at 4 different frequencies to disentangle the CMB. Here's an artist's conception of what the telescope will look like. The one on the right is real. The 2 on the left are Photoshop, very important technology in modern physics. I always like to advertise, although it's past our application deadline for grad school, nevertheless, we're always looking for talented people to come and help us in San Diego and Berkeley and elsewhere. And we're really going deep with the CMB to reveal what the mass of the neutrino is. That's one of our 2 primary goals. First goal is gravitational waves. Second goal is neutrino mass. Third goal and fourth goal are primordial magnetic fields and cosmic polarization rotation, testing fundamental physics at the deepest level. Here's kind of a cool thing. It turns out there's a LoJack system for boats. So Jim, if you're looking for a boat, when Archimedes has a little free time, you can send a boat like this out to go and pick up your telescope, and you can track where it is. Here's where it is in real time. You can actually track where your $3 million investment is traveling currently. So we're on our way to Cartagena, Colombia right now, and then it'll go through the Panama Canal, and then it'll emerge on the other side. Then we have to drive it from sea level to almost 18,000 feet. It's quite astounding what experimental physicists have to go through. The community itself is uniting behind a push to measure these signals from inflation, from neutrinos, and from this forbidden effect, this Chern-Simons effect. We're attempting to measure these with exquisite accuracy. That has this really, they should have let me come up with the acronym for this. We just call it CMB Stage 4 or CMB S4. Kind of boring. But here's us I'm in the back row somewhere. This is in Michigan. We're having another meeting in Berkeley. A lot of partnerships are expected to emerge in Europe. But really, it's exciting for me because it's the first time the DOE, Department of Energy, is investing in CMB physics. So they're interested in dark energy. But where is the most awesome particle accelerator in history? It's the Big Bang itself. We can test things that traditionally could only be done in particle accelerators like the LHC. Now we're trying to do that with the universe itself, the ultimate LHC, the ultimate laboratory for physics. So we have a time scale that the Department of Energy is pushing to measure these properties of neutrinos, gravitational waves, and fundamental physics like dark energy and polarization rotation. And we're having many meetings like this. The next one is in Berkeley in March. I'm hosting another one in June in San Diego after the American Astronomical Society meeting. And really what I want to leave people with today are these different points. We're now at a point, when I first thought of doing B mode, looking for B modes from inflation, people were very suspicious of it because it was so hard to do. But my colleagues are so talented at building these detectors that work near absolute zero, under almost zero pressure, at the highest altitudes possible on Earth and in space. We've really exceeded Moore's law. We're now able to do things that Moore's law would have underestimated us being able to do. So it's really exciting to work in a field like this with very smart students and postdocs, et cetera. And what we're trying to do, I think, is the biggest physics of all. And that's why it's so exciting to be in this field. And it's a real pleasure to be here. And so I want to thank people for coming. And I'm happy to answer any questions.